Hi everyone, and welcome to your first lesson of National 5 Computing Science here at Woodmill. As I said in the introduction video, the first unit that we're going to cover is computer systems. What I'm going to do is give you a quick overview of what this unit of work entails. So there's 4 sections, which are data representation, computer structure, the environmental impact, and then security precautions. Within each 4 sections, we have a separate pieces of work. So we've got binary and denary conversions, floating point representation, ASCII representation of text, vector graphics, and bitmap graphics. Within computer structure, we have the 3 parts of the processor, memory locations with unique addresses, the data and address buses, and high-level language translation. Within security then, we have firewalls and encryption. Okay, so from now until summer, this is everything that we're going to cover. Okay, so today's lesson is going to be in data representation, and it's going to do with binary and denary conversions. So denary is a word for a positive integer. You may have heard them being referred to as decimal in S3 as well. So our normal counting system is known as denary, which means base 10. We count in tens because we have 10 fingers. Our system has 10 separate digits to represent every single number we can think of. Now remember, in computing we start counting from 0, so the range 0 to 9 actually contains 10 numbers, hence the base 10 system. We have to reuse these numbers to get bigger numbers. For example, when we run out at 9, we use 10 to represent the next number. Here is how we represent a big number in base 10. So the example is 65,536, but it's actually really made up like this. So we've got 6 pieces of 10,000, 5 pieces of 1,000, 5 100s, 3 tens, and 6 ones or 6 units. So all of those combined gives us the full total of 65,536. Always remember that the unit is over on the right hand side. Now that will come in really handy for denary to binary conversions and vice versa. So binary is a positive integer. It's the counting system that electronics, including computers, use, and it means base 2. Binary only has 2 separate digits to represent every single number that we can think of, and it's 0 and 1. Now many of you will remember this from S3, so I'm going to give you just a quick recap on what binary is and how we convert. But for those who maybe haven't seen it before, not to worry, there's going to be plenty of theory, okay? So we have to reuse these numbers to get bigger numbers. For example, when we run out at 1, we use 10 to represent the next number. Now 10 in binary is actually the number 2 in denary. All numbers consist of 1s and 0s. A computer is a 2-state system. Computers count in 2s because everything inside the computer is represented by on and off. So that's the presence or absence of power. We can therefore use binary to represent this. 0 means absence of power and 1 means presence of power. So to understand binary numbers, we use the same breakdown as shown for denary. Now converting a binary number to denary is done like this. So let's take an example, okay, a binary number of 10101111, and we want to convert it into denary or into decimal, okay. So along the top, okay, we have the 8 bits of our byte, okay. So we've got 128, 64, 32, 16, 8, 4, 2, and 1. Okay, and these 8 bits represent a 1 byte number. So what we do is then translate this binary number underneath these headings. Okay, so I've just copied 10101111 underneath these headings, and that then gives us the sum. Okay, now anywhere that we have got a 1 written, we add that to the sum. So you can see 1 is underneath 128, therefore 128 is the first number I'm going to add to the sum. The second number in our binary number was 0, which is under 64, and because it's a 0, we don't add it to the final sum, as shown here. 32 has a 1 underneath it, and therefore we add that to the sum. 16 is empty, so we don't add that. There's a 1 underneath 8, so therefore it gets added to the final sum. The same goes for 4, for 2, and for 1. And therefore, we end up with a denary value of 175. Now, a really good way to check if you've got this conversion correct, okay, is to make sure you've copied the binary number correctly under your headings here, okay, and then wherever you have the 1, just add up these placeholders, okay, so quickly add up on a calculator 128 plus 32 plus 8 plus 4 plus 2 and plus 1, okay, you should then get 175. So always remember that the unit is over on the right hand side, as I said earlier, okay, so the units are always over on the right hand side. If I want to convert the binary number 101 to denary, don't automatically think that it's 101 across here. We always start from the right hand side, okay. So we've only used 3 bits here for this binary number, and therefore it only uses the first 3 bits, 1, 2, and 4. So 101 in binary is 4 plus 1, which equals 5. The reason we didn't add 2 is because there's a 0 underneath the header. Now, always remember that the unit is over on the right hand side, as said before, okay? If I want to convert the binary number 10111 to denary, I simply fill in the first 5 bits here, so 10111. I will then write my sum underneath, okay, so it's 1 multiplied by 16 because we've got 16 here, plus nothing in the 8 column because it's a 0, plus 1 times 4, plus 2, plus 1. There's our final sum, and therefore the value is 23. So the binary number 10111 converted into denary gives us a value of 23. If I then want to convert 110100, I simply put that into the table here underneath my headings. Notice this is a 7-bit number because we don't have the 128 filled in, okay, so this is a 7-bit number, which is what you'll have seen in S3 as well. We then calculate the sum, write out the sum underneath, and get our total value of 116. Again, the way we can check this, okay, is to ensure that we've copied the binary number across correctly, and then wherever we see a 1, we just simply add up the placeholders, so 64 plus 32 plus 16 plus 4, 64 plus 32 plus 16 plus 4 will give us a total of 116. Now, denary to binary conversion is simpler. Okay, so just try to fit your number into the biggest placeholder it will go. Convert the denary number 85 to binary. Okay, so just like binary conversion, we draw out our table. Okay, so the 8 bits starting with 128, finishing at the unit with 1. 85, okay, is the denary number that we want to convert to binary. So what we do is we take 85 and check if 128 fits into 85. Okay, 128 is far too big to fit into 85, so we put a 0. We then move on to 64. Now, does 64 fit into 85? It does, and therefore we put a 1. Okay, because 64 can fit into 85, we put a 1, and we take the remainder, so 85 minus 64 gives us 21. Therefore, that's the number we're working with for the rest of the conversion. Okay, so does 32 fit into 21? No, because it's too big. So then we move on. Does 16 fit into 21? It does. So we put a 1. 21 minus 16 gives us 5, so 5 is the number we're now working with. Does 8 fit into 5? No, it doesn't, so we move on. Does 4 fit into 5? Absolutely, so we put a 1. We are then left with 1, so 1 is the number we're working with now. Does 2 fit into 1? Nope, so we put a 0, and we're left with the 1 which goes under our units tab here. Okay, so there you'll have seen by that process of elimination that we have our binary conversion complete. So the 8-bit binary number for Denary of 85 is 0101 0101. And again, the way we can check that is to add up wherever we've put our ones here. So if I add up 64 plus 16 plus 4 plus 1, that will give me the total value of 85. And that's how we do denary to binary conversion. Okay? And there we are. Now, 8-bit binary numbers, so unlike our denary numbers, sometimes binary numbers must have leading zeros. Okay, so 0001 1101. This is because binary numbers travel around the computer system on collections of wires called buses. These collections of wires will all have a value as far as power on or power off is concerned. These values change as the pulses of power travel along them every clock cycle. Okay, so this is an 8-bit bus. 8-bit numbers must have 8 digits, so may have zeros at the beginning.